Yeah, this topic, we may have a few questions, so usually relatively hard questions. We may need to apply this technique. Yeah. From the name, you can see what we are going to do. Merge. Now we are familiar with the merge operation, right? Given two ordered arrays, now we want to merge them to get one whole ordered array. That's the full complete merge. But here we do partial merge. From the name you can see. We do not need to completely merge those two ordered arrays. Just a partially merge. Because the reason is, why partial merge, not a full merge? Yeah. So the reason is very simple. For the full version, the goal is sort, right? Sort the array. Yeah. If our goal is not sorting the whole array, we just want to find one special element. Kth smallest or kth largest, that's the selection problem, right? Yeah. So in that situation, you can see we do not need to sort the whole array. So for the selection problem, kth smallest or largest, then we do not need to do the full merge, only partial merge. The idea is very simple, but you will see many times the result is pretty good. Yeah. How good it is, the second half of this topic, I will show you how good the result will be. All right. Oh, my remote control, I need to connect. So then I can control it. All right. Yeah. Now, let me look at that topic. Yeah. All right. Let's look at a simple question first. Yeah. When we start, we look at a simple question. Yeah. Given a 6-element array, all right. The goal, we want to find the third largest element. That's a simple question. Okay. Oh, I need to give you a condition. 6-element array with condition. Yeah. Otherwise, yeah, although we can do without condition, you need to do a lot of work. Yeah. So here I give you a simplified version with x1 less than x2 less than x3 and x4 less than x5 less than x6. Two ordered chains. With this kind of given condition, the problem is much easier. Yeah. All right, let's look at the solution. So here I draw a diagram. The first ordered chain, then the second ordered chain. So here, it's a typical merge situation, right? Yeah. The data arrangement, pretty much the merge situation. Yeah. But here, we do not need to solve. So we only need to find third largest. So we want to use the minimum number of comparisons to find the third largest element. Right? Yeah. So here, there is a simple idea, the partial merge idea. Yeah. Pretty simple. So we run the merge operation, but in a partial way. We do not need to complete the whole merge operation. As soon as we get the third largest, we stop immediately. Yeah. We have the third largest, then we stop. So when we start with the comparison at the high end, yeah, larger end. Yeah. This larger end. Okay? Yeah. So the first comparison, we can get the first largest. Second comparison, second largest. Third comparison, yeah, because based on our understanding of the merge operation, each comparison results in one element in place. Yeah. But this time we from the larger side, still one element in place, right? So the largest in place, second largest in place, then third largest in place. Right? This is our solution. So we stop. Yeah. So for this question, the answer total 3 comparisons. Yeah. This is a simple example. Simple example. All right. But the next question, some of you may want to ask, if it is optimal or not. It is simple, but how do we know this solution is the best, right? Yeah. Yeah, let's look at this question. If this solution is optimal or not. Yeah. The answer is sometimes it's optimal, but sometimes not optimal. Yeah. So usually for relatively simple questions, it is optimal. But for relatively harder questions, not optimal. Yeah, definitely, yeah, not optimal. Yeah. Yeah, but here I want to show you the evidence, yeah, give you some more information so you can, give you more background for your understanding. Yeah. All right. To see this optimal or not, we need to apply a formula. Remember last time I gave you a formula. The lower bound formula for comparison sorts. We have that formula. So we start with this formula. Right? So lower bound formula for comparison sorts. Comparison sorts. Yeah. All right. The formula is ceiling function of log base 2 n factorial. Yeah. Lower bound, so worst case, the number of comparisons needed for the worst case greater or equal to this number. If your sorts reach this number, then we can say it's optimal. Yeah. You hit the lower bound. That means your algorithm is optimal. But another question, if you cannot hit this lower bound, your solution is a little worse than this lower bound, does that mean your solution is not optimal? Think about this question. Sometimes you may not be able to reach this lower bound. That could happen. You may not be able to, because it could be very hard. When n becomes larger and larger, when n is small, it is relatively easier to get this lower bound. Then, when you grow this n larger, then it becomes harder and harder to reach this lower bound. Yeah. Then, now this question. Actually, the answer is still unknown. The answer is unknown. That means, is it always possible to find a sort that can reach this lower bound, hit this lower bound? That answer is unknown. Yeah. All right. Now we want to extend this lower bound formula to cover our current case a little more. Currently, we have some partially ordered subarray in our data. So we want to extend this formula to cover that situation. So then we can study more cases. All right. To do that extension, we need to go back to, in our last lecture, we learned that decision tree method, right? We need to recall, we need to apply that decision tree method. Because we use decision tree method, we derive this lower bound formula. Now, our data slightly different. So we need to modify our decision tree. We need to add this ordered chain information in our decision tree structure so that we can update our lower bound formula. All right. Here, let me write the updated version. All right. Given an element array. It is known that there is a k element ordered subarray. k element of the subarray. Yeah, we know k less than n. All right. Question: what is a lower bound? Because lower bound, we can have many different lower bounds, right? Although we want to find the best lower bound. Yeah, but here, let's just say we find one lower bound. Right? That question. So this new information should help us reduce the number of combinations, because we do not need to do the same number of comparisons if this condition is not given. This condition is not given, we need more comparisons. Now we have this useful information, so we should significantly reduce the number of comparisons. All right. To answer this question, we need to draw a decision tree for our current data. Yeah. Decision tree for any algorithm that sort this array. Yeah. Decision tree is not for data. Decision tree is for algorithm. Yeah. So draw the decision tree for a solution. Okay. Yeah. We know it can be drawn. Yeah. All right. Now, when we draw, we need to draw vague version, right? Because too much unknown information. It is very hard to draw accurate decision tree. Some rough, vague way to draw decision tree. So the data and elements. All right. Then k element subarray k could be arbitrary subarray, right? Could be arbitrary subarray. For our convenience, can we just assume the first k element subarray equivalent? We consider the simplest case here. First k element. No problem, right? If arbitrary, can we just group, right? Group the elements in the ordered chain, put them in one group. Another way, can we relabel them? Yeah. So these n symbols, original symbols, can we use kind of variable substitution to relabel them? To change the symbols? Not big deal, right? Just call them different names. So we have many different ways we can do, but for convenience, let us assume the first k elements are ordered. That's for convenience. Not just for convenience, without loss of generality. Yeah. So we do not change the difficulty of the problem. Same problem. Yeah. All right. Now we are ready to draw that decision tree. Some pretty abstract decision tree. We know each node represents some comparison, right? Because we need to make decision. All right. Yeah. It's a binary tree, decision tree. All right. But how do we represent this part? This ordered subarray, that means we do not need to do any comparison to order this part of the data, right? No comparison needed. Okay? See? No comparison needed to order this portion of data. Right? Yeah. Yeah. They are ordered. They are ordered. All right. But in our nodes, how do we reflect it? Right? Yeah. Because our node, each node carries the current ordered information, right? Yeah. Carries the current ordered information. Okay? So when we go down everywhere, the current known ordered information is carried from top to bottom. All right. So you can imagine in each node that x1 less than or equal to x2, this part of the data is carried from beginning to end. Then other places, other part, every time you do comparisons, you add more ordered information to your data, right? Yeah. But this part, pretty much fixed, right? This part pretty much fixed. All right. Yeah. All right. Then, when you reach the bottom, that's the final sorting result. All the elements are ordered. Yeah. So this part is embedded. This ordered subarray is embedded in the final ordered array, right? Yeah. Mixed, embedded. Yeah. All right. Yeah. Yeah. So you have some mixed embedded way could be complicated, right? Could be complicated, mixed. It's hard to draw the specific order information. We don't need that. Yeah. All right. But if you look at these particular elements, yeah. So among these elements, no comparison work. Yeah. That's our observation. Now we need to interpret this observation. Interpret it. Interpret this observation in our formula. All right. How to interpret? Yeah. So for this part, let's compare two cases with this part and without this part. Yeah. Compare these two cases with this information and without this information. What is the difference? We can get an idea. Okay? All right. First, let's look at the without. Without this partial ordered subarray, then the total number of leaves. We know leaves means the sorting results, right? Sorting results equals n factorial, right? Yeah. Yeah. Although, remember last time we include the greater case, greater means the algorithm is redundant, right? Redundant. Equal case, not redundant. Yeah. Here, let's just consider no redundancy, all right? No redundancy. Redundancy. No redundancy, yeah? Because we want to find the best algorithm. Lower bound, we want to find the best algorithm for the lower bound. So we do not consider the redundancy case. Yeah. So that's, we only consider this equal case. All right. That's the without case, the leaves. Now, let's look at the with case. With this case. So this condition, how much improvement this condition can help us to get better efficiency. Yeah. All right. So let's look at the among these n factorial. What's the meaning of n factorial? N factorial permutations, right? Remember last time we used the permutation. We use the permutation to model the results. Model. Sorting results. Because permutations very simple, right? Yeah. The permutation, just the n different numbers. Usually we use n natural numbers. First n natural numbers, consecutive, from 1, yeah, not 0, 1. So we use the symbols 1 through n. Yeah, permutations. All right. Then k of them, k of the elements are ordered, right? K of the elements are ordered. That means in our permutation, we fix first n elements. How about that? Yeah. So we have a general n permutations. Yeah. N permutations. All right. Yeah. So the symbols inside, we can do a lot of permutations, right? Yeah. But with the given condition, with this given condition, yeah, for convenience, we fix. Well, that means 1, 2, k. We never change them. When we do permutation, this part is fixed. Fix this part. The remaining part we can do permute, right? We can permute the remaining elements. We are only allowed to do remaining permutations. Yeah. Actually more than that. Yeah, actually more than that. Yeah, because so here, this is a special case. Yeah. Yeah, actually, yeah. Because this special case does not cover all possible such cases. Because when we talk about permutation, we need to consider all possible such cases. This is just one special example. Cases. Yeah. All possible, what do you mean all possible? These fixed elements can appear everywhere. Not the first consecutive location. First consecutive is just one of the cases. All right. So there are n positions. The selected fixed elements can appear in arbitrary k positions. That's all cases, all possible cases. Yeah. All right. So here, our understanding. To get an exact, accurate understanding, we need to think in this way. Yeah. Select arbitrary k positions. And fix them and then do permutations. That kind of process. That kind of process. Okay? All right. Yeah, pretty messy. Yeah. All right. Yeah, because this is the relatively hard part in our analysis. This part very abstract. We need to use a lot of imagination, intuition to understand. Yeah. Anyway, yeah. What I want to say is, all right, in that n factorial permutations, there are k of them, there are k of the positions, yeah, there are k elements. The permutation of those k elements are treated as one case. Okay, all right, because those k elements, yeah, the k elements here, we know these k elements can give us k factorial permutations, right? K factorial permutations. K factorial permutations, but our given condition fix the order of these k elements, right? Our given condition fix the order of these k elements. That means all these k factorial permutations are treated as one case. All of them treated as only one case. Only one order is allowed for these k elements. How about that? One case, one order is allowed for these k elements. That means the k factorial, this k factorial is treated as one, so that means our n factorial, we need to do division by k factorial. Yeah. Then that's our total number of permutations with the given ordered information. Given ordered information. Think about that. Yeah. Yeah. So that's the way. So if we draw a decision tree, this part, so we will not have the same n factorial number of leaves. So the new number of leaves should be n factorial over k factorial. Because that's the real number of different sorting results we will have. Okay, same number of leaves. All right. Now we can make our conclusion, the formula. Yeah. All right. Now the final formula. Lower bound formula. We update lower bound formula. Okay. New lower bound formula for that special condition given. That is, so I do not need to write a lot of words. I just give you the formula directly. Still seeding function, log base 2. But inside n factorial over k factorial. That's our lower bound formula. Yeah. So we use the same method. Remember. So if I recall, yeah. So if some of you couldn't jump to this step this fast, let me just use the method we recall the method we used the last time. Remember, so our decision tree, it's a binary tree, right? It's a whole binary tree. Remember the height, little h, the height corresponds to number of comparisons for the worst case. All right. Then number of leaves, remember, number of leaves, we use capital L. Yeah. And we derive a formula 2 to the h greater or equal to L. Why? Remember, we use complete binary tree. Complete binary tree. Complete binary tree corresponds to the equality case. Equality case. Then, for non-complete binary tree, the number of leaves can only be smaller. So for that reason, we have this inequality. Okay, all right. Now, this time, 2 to the h, worst case, the height of the decision tree, this time we have this. Number of leaves, that's n factorial over k factorial. Okay? Yeah. Then we get this seeding function. All right? Yeah. So that's our new version of lower bound formula. Sometimes this formula you can use. All right. Then another version. Yeah, because this is just one version. We can generalize this idea, right? Yeah, you can generalize this idea. All right. Now let's generalize it a little bit. Generalize the idea or method. analysis, the whole thing. We generalize. Generalize in which way? All right. Given an array, 1, 2, n element array. Right. Now, our condition, the given data is like this. The first portion, the first subarray, sub 1 ordered with A elements. The size of first subarray. The size of second subarray, sub 2, ordered, also ordered, but with the size B. Yeah? So 2 ordered subarrays. Now we generalize. We generalize to this case. Yeah. So in this case, the lower bound formula becomes, you can do it by analogy, log base 2, n factorial, denominator A factorial times B factorial. Yeah. Lower bound. Yeah. All right. Yeah. 3 ordered, more ordered, you can use this way. Yeah. But the idea is clear. We can use the same analysis. All right. Yeah. So then, based on this, let me show you the result. All right. Yeah. So first example. Question. Yeah, I just write the minimum words, number of words, 6 array. Yeah, so you know the meaning. 6 element array with what? With x1 less than x2 less than x3. I feel a little slow. x3. Okay, all right. Then I will go sort it. Yeah. Minimum number of comparisons to sort it. Right. First, let's estimate it, because apply this lower bound formula, we need to estimate the lower bound. Ceiling function log base 2, 6 factorial over 3 factorial, right? Log base 2, cancellation, right? 6 times 5 times 4, right? 6 times 5 times 4, the tail part cancel out. Yeah. 20, 120, right? To 120 equals 7. Yeah. All right. So the lower bound, 7 comparisons. That means if you can find a solution with 7 comparisons, then your solution must be optimal. Nobody can do better than 7 comparisons. But the next question is it possible to find a solution with 7 comparisons? That's another question. Possible or not? Okay? Yeah? All right. That's another question. All right. Then, let's try it. Yeah. Because, so one possible problem in homework assignments in my previous students, not you. So I haven't, because we haven't got there. Yeah. So not your class, yeah. Previous classes. So when I give you question, our typical problem solving questions, all my questions, I ask you to solve, to sort, find the median, what I want to know, you need to tell me how to do it, right? Yeah. So as our computer science students, we need to find a solution. Solution means we need to know how to make it happen, right? Yeah. But many students, they just give me the estimate number. Here, this is the estimate number. But how to use the 7 comparison to do it? Nobody knows, right? Yeah. Because you use this lower bound formula. You do not need to know how to make it happen. Yeah. So that's a common problem in some of the students. Yeah. So what do we need to do? The estimate, just to give us some basic information we can use to reference, to give us some guidance. But that's not a complete solution. Yeah. Keep in mind, that's not a complete solution. The solution, you need to tell me, what are those 7 comparisons? Comparison 1, so what element, which element, yeah. So that's a, common error. Another common error in your class, I saw many such problems in your class. Many students, when they write their solutions, they just give me a list of comparisons, but no discussion. No detailed analysis on all different cases. Just give me a sequence of 7 comparisons. That's not a solution, right? That's not a solution. Because you do not talk about all different cases. Solution is, if based on your steps, the steps you give in your solution, we can write a program to solve the problem. That's the solution. That's a valid solution. But you just give me a sequence of comparison detail steps, right? Steps. But I cannot use those steps to write a program, right? The logic is not there, right? I need to use the logic to write a program. So that's pretty common in your solutions. We need discussions. All right, yeah. So that's just some comments related to your homework. Yeah. I hope in your second assignment, so you can try to do more than that. At least do part of the useful work, right? Yeah. Part of useful work. Yeah. All right. Yeah. Now, let me talk about solution. Yeah. I run out of space. I just put 3 empty slides, yeah, but I need a little more space. Yeah, probably. Yeah, here I have some space to use. Yeah, because I need to talk about a little more information here. Yeah, all right. Yeah, we need to continue that question, right? we need to continue continue that question. Okay. All right. All right. That question. All right. Yeah. x1 less than x2 less than x3. All right. Then x4, x5, x6. No information, no order information regarding these three elements. All right. Then, let's sort it. Sort these three elements, or sort this subarray. We know we need three comparisons, right? Three comparisons to get sorted. All right. After that, we have two partially ordered subarrays, right? Two ordered subarrays. 3, 2, 1, 3, 6. Sorry, 6, 5, 4. Okay. Matching our typical merge situation. Then we merge. How about just merge them? Merge the worst case 5 comparison. Okay? Yeah. The merge step 5 comparison. So total, this method total 3 plus 5, 8 comparisons. 8 comparisons. Yeah. Now you can see one worse than that 7 comparison, right? Because that's the, lower bound. That one is lower bound. The lower bound is not guaranteed. When we have a lower bound, that means nobody can break this lower bound. That's the only meaning. Nobody can do better than this lower bound. If the if this lower bound is reachable or not, nobody knows. Nobody knows. So this solution just one comparison worse than the lower bound. It could be an optimal solution, but it's unknown. Yeah. We don't know. Yeah. Yeah. So that's the, because with this lower bound, how good is your solution, right? How good is the solution? Just the one worse than the lower bound. There is a possibility the solution is optimal. Just we need to do a lot of work in order to know the answer. We need to do a lot of work. So it is still unknown. That part is unknown. Because that part could be very hard. I don't know the answer. It could be very hard. Yeah. That could be, our future study. Yeah. So here, just give you that information. Okay? Yeah. All right. Yeah. So with this information, because this method, you can see it is quite useful. Yeah. So today I spent quite some time to talk about this topic because in your second homework assignment and also final exam, you have pretty good chance to see some relatively hard questions. You need to use this method. Several. Okay? All right. Yeah. Here, when you have situation like this, remember last time, in our homework assignment number 1, the last question is very hard, right? Question number 25. So we have 3 different versions of solutions: weak solution, standard solution, and a strong solution. Strong solution, we don't know if we can find it or not. Yeah. Sometimes the standard solution, we don't know. Yeah. So here I want to talk about that. I want to give an example to show you the difference between weak solution and standard solution. What's the difference? Weak solution. Because then in your homework assignment number 2 and final, you may have the situation because sometimes the situation, standard solution could be very hard, then you just target the weak solution. The difference is only 1 point. 1 point difference. But usually weak solution is much easier than the standard solution. Yeah. Here, I want to give you an example to show you. To show you the difference. Yeah. Let me get my example. I write it on my scratch paper. Yeah. On my scratch paper. Yeah, so. All right. All right. Yeah, here. Yeah. The question. Yeah. Question like this. Yeah. Yeah. So let me recall a little bit. All right. Yeah. So the question here. Okay. All right. All right. 7 element array. With information x1 less than x2 less than x3, x4 less than x5 less than x6. Okay. You need to find the median. Yeah, that's the question, right? All right. All right. Yeah. Here I give you 2 solutions. The first one, weak solution. Second one, standard solution. Yeah. So you get an idea. What's the difference? All right. First, weak solution. The weak solution is usually not too hard. We just use some not fancy, just common techniques. Yeah. Common techniques. We do not do any special or smart way to arrange the data. Yeah. We just do, normal, straightforward way to arrange our data. Yeah. In general, relatively easy to find this version of solution. Standard, you may need to do some special and smart data arrangement. Not trivial. Yeah. So here, I'll give you two versions. You can compare the difference. All right. For this weak version of solution, 2 ordered subarrays, right? All right. But we have X7 there. Yeah. X7. Yeah. All right. So let's do this way. Yeah. Our normal operation. The first ordered chain. Now I have X7. Let me do binary insertion. How about that? Binary insertion. We know we need 2 comparisons, right? After 2 comparisons, we get X7 inserted into this ordered chain, and we grow the ordered chain to 4-element ordered chain. Right? Yeah? So now the result, this time 4-element ordered chain. X7, X3, X2, X1. But we have another 3-element ordered chain, X6, X5, and X4. Our goal, we want to find the median. The median is 4th largest or smallest, largest, but either side, the 4th, right? So that means you need 4 comparisons to find a median. The first step you need 2, second step you need 4, total 2 plus 4, 6 comparisons. Yeah. So this weak solution, you use 6 comparisons. You can find a solution. All right. Then strong solution. Now, strong solution you need to improve, right? So your target, you use 5 comparison to find the solution. That's the strong solution. Oh, okay, no problem. Ciao. Yeah. So you can watch the video later. Yeah. Don't worry. Yeah. All right. Yeah. Now, strong solution. Yeah. My space quite limited. So let me do the strong space here. Standard. Yeah, standard. And not strong solution. Standard solution. Oh, sorry. Standard solution. All right. So here, all right. Standard solution, the first comparison, let's compare here. This is our first comparison. Okay. So because the data is symmetric here, right? So we can assume one is greater than the other. Yeah. So let's assume X5 is greater than X2. Symmetric. Yeah. So we pick one of the 2 cases. So we get a longer ordered chain, X6, X5, X2, and X1. All right. Then X4 lower than X5, and X3 greater than X2. So that's our new diagram. All right. Then we do elimination. So with this diagram, let's do elimination. Here. All right. Fourth largest, right? Yeah, because median is the fourth. Largest or smallest, fourth, either side. Smaller side, L side, two sides. All right. Look at the x1. x1. Can we find 4 elements greater than x1? x6, x5, x2, and x3, right? So 4 elements are greater than x1. So x1 is eliminated. Okay. Then another one, x6. Can we find 4 elements smaller than x6? x5, x2, x1, and x4, right? Yeah. So x6 also eliminated. So we can eliminate 2 elements from consideration for the median. Remaining elements, let's look at the remaining elements. After elimination, remaining 5 elements, right? Yeah, there are 5 remaining elements. But we need to keep the known information. x5 here, x4 here, another small ordered chain, x3 here, and x2 here, and there is another a link between these 2 elements. That's the known information. Then x7 unknown. All right. So in these 5 elements, we need to find a median. So median of this 5 is the median of the original 7-element array, right? Yeah. So the local median, so here, local median of these 5 elements equals the global median, right? Yeah. Global median in this situation. All right. How many comparisons do we need to find this local median with the given information? Yeah. We have here, we need to use our median of 5 result. We have the median of 5 result, right? Yeah. So remember, yeah. That is a median of 5. We have the median of 5 result. So let us apply this median of 5 result. Given 5 elements, to find a median, we need a 6 comparison, right? Yeah, that's our result. 6 comparison. Now we know how to do those 6 comparisons. So here, here, look at the given information, this part. How many comparisons the known information can help us save? We can save a few comparisons by the known information. All right. So here the known information, yeah, if we ignore this link, yeah, we ignore this link. Yeah. This link may help, yeah, but for simplicity, let us ignore this link between x5 and x2. After we ignore this link, at least we know the comparison results of these 2 pairs, right? And we know the comparison results of these 2 pairs, both are useful, right? So both comparison results are reusable for median of 5, right? So these, because this information reusable, equivalent to the 2 comparison, right? Yeah. If we recall the method we use to find median of 5, we do tournament method, right? Yeah, we do tournament method on first 4 elements. Here, these 2 results, that's part of the tournament method, right? Yeah? So both of them are reusable in the tournament method. So that means 2 of the 6 comparisons can be saved by the known information. That tells us if we find a median of 5 based on this given information, we need 4 comparisons. Okay? So the second step, we need 4 comparisons. But the first step, this step, 1 comparison. So the total 1 plus 4 equals 5 comparisons. Yeah, sorry, very messy. Yeah, pretty messy. Yeah, yeah. Hope you can. But yeah, if you follow all the way here, you can understand. Yeah. So this tells you the standard solution. Yeah. Definitely, you need to do some extra work. Yeah. Non-trivial extra work. Then you can improve your solution from 6 comparisons to 2 comparisons. Think about that difference. Yeah. So this example, I want to show you the real difference between these 2 versions of solutions. So you can choose. Yeah. Yeah. If you can find the standard solution are already very good. Yeah. Strong solution, we target the 7 comparisons. We may not be able to make it happen. Yeah. Too hard. Yeah. We target the 7 comparison solutions. We may not get it. Yeah. That's why it is extremely hard. Yeah. All right. Yeah. So that's about this topic. Yeah. All right, let's take a break at 7 o'clock. So we start